Aloha and welcome to our video on the study of light. In this video, we'll describe the waves that compose the electromagnetic spectrum, we'll describe what different types of spectra reveal about the stars, and finally we'll explain how the Doppler effect is applied to the motion of stars in relation to the Earth. So what we see here is a picture depicting the entire electromagnetic spectrum. We have our short waves down here, our radio waves like our AM, our TV, our FM, the waves used for radar, infrared, which we kind of sometimes mistake as heat, the visible light spectrum, which we see down here, our ultraviolet rays, X-rays, and gamma rays. So we can see an incredible spectrum of waves. We organize them by wavelength. So we'll notice that our gamma waves have 10 to the minus 12 meter wavelengths, versus some of our AM waves are going to have a wavelength that's going to be of about 10 to the fourth. So we can see a huge disparity in the length of the wavelength, and that's what kind of gives us these different properties for each. For visible light, notice that our spectrum is down here from about 400 to about 750 nanometers. Those with the shorter wavelengths are going to be your purples, and our longer wavelengths are going to be our reds. So the entire electromagnetic spectrum is here. What we're most familiar with is going to be our visible light, and then, like I said, some of our radio waves as well. Now, one thing I want to talk to you about when we talk about studying light is this duality, this wave-particle duality that we have. The wave nature of light, okay, is the determining factor for wave motion's ability to produce the interference pattern. So what that means is that if we shine light onto an object, then we can get an interference pattern that makes us suggest that light is actually a wave, these electromagnetic waves. But we also have the photoelectric effect. And that means that electrons being emitted from the surface of a metal given by the incidence of radiation. So if we shine light onto a metal, it knocks off electrons. And because we have that knocking off, then that tells us that we have a particle nature of light as well. So light's really bizarre. We don't know, we can't say it's a definite wave, we can't say it's a definite particle, but what we can say is that it has this duality. It has a little bit of both together. Okay, so let's talk about the formation of spectra. For all of these, what we're going to do is we're going to take some source of light and we're going to shine it through a narrow slit into a prism here, and then we'll see what gets projected outwards. For a continuous spectrum, what we have is our incandescent solid, so a light bulb basically. And what that's going to do is heat that solid up until it starts emitting light. That light is going to transfer through the little slit, like we said, through the prism, and it's going to project a continuous spectrum. So we can see that this solid is emitting light on every wavelength, and that's kind of interesting for us. So if we have this incandescent solid and it emits out that light, it's going to throw out this continuous spectrum. Now, we can do things with this. I can take this solid light that we had before, this incandescent solid, we can shine it like we were, but before we get to our narrow slit, we're going to run it through a cool gas. That cool gas is going to absorb some of this energy, and what we can do is when we run it through and we project up our spectrum, because we're absorbing energy, we have what we call an absorption spectrum. This absorption spectrum is going to show up as that continuous spectrum, but you'll notice that there are wavelengths that are missing, and these are shown by distinct black lines. So that can give us an idea of the nature of the gas that we are shining it through. Different elements are going to absorb different wavelengths of light, and then through this absorption spectrum, it shows me what that gas is made up of. So if we take this to astronomy, if I have a star that's emitting light, as that star is emitting light and goes through a cloud like a nebula, I can see what's in that nebula by looking at this absorption spectrum. Now conversely, if I take a gas and I heat that gas up, that gas, when it heats up, is going to release out energy, or these wavelengths, and then when we run the light from that heated up gas through that slit in the prism, we end up with an emission spectrum. And an emission spectrum is going to give us just these lines. So again, different elements are going to be a little bit different. So by looking at either the absorption, if we have a light source shining through that gas, or if the gas is hot enough to be emitting light on its own, let's say a star, what it gives us is the ability to look at this emission spectrum and see what elements are being represented there. Now, one of the interesting things that we notice with light is it does behave like a wave. So we've heard of the Doppler effect before, and the Doppler effect says that if I have sound and the sound is being emitted by a moving source, and I have two observers, so our sound is the siren on the ambulance and it's moving, we have two different observers or the same observer in different locations relative to the source. Prior to the source, prior to the ambulance coming, it's going to be a higher frequency. And the reason for that is as it's emitting out the sound waves, they seem to be getting squished together. So our frequency goes up, it's a higher pitched sound. Once that source travels by, it's going to be emitting out the same waves, but they kind of get stretched out a little bit, so it'll be a lower frequency. So that's why you notice as a car is passing you, it'll kind of build up to a higher frequency, a higher pitch, you'll hear it going, and then passes you, it goes like that. And that's this Doppler effect. Now, Sir Edwin Hubble was looking at stars and he realized that these stars that he was looking for had a shift in their visible spectrum to the red. And what that did is that meant that the wavelengths were getting a little bit longer. We knew what the stars were made of, we knew what they were burning, but when we looked at them, the absorption was a little bit off, and we call this the red shift. And the net result of this was that by looking at these stars and seeing a shift to the red, that would mean that these stars are moving away from us. So it gave us an idea of where the stars were going. So we could look at a star, if it was shifted towards the blue, the frequency was getting bigger, they would be coming towards us and we'd be worried about a collision. If we see the stars moving away from us, then that would mean we're moving further apart. And by noticing this throughout the universe and what we could see, we noticed that there's just a lot more of this red shift. And the only way to explain that would say that the universe was expanding. But we'll talk about that a little bit later on in this unit. Okay, that's it for our video. As always, good luck on the quiz, and we'll see you in the next video. Aloha and welcome to our video on tools for studying space. In this video, we'll explain how refracting, reflecting, and radio telescopes work, and we'll end with a discussion on the advantages that a space-based telescope has over Earth-based telescopes. So the first type of telescope we're going to look at is a refracting telescope, and these type of telescopes use a lens. And what a lens does is it bends or refracts the light. So if you see in our picture, we have light coming in through the opening here. It's going to hit the lens and it will be bent to this focus here. So you can see the light waves coming in, they hit the lens, they're kind of bent here, they're going to pass through a little bit further, and then we have an eyepiece lens down here to kind of straighten them out so that our eyes can see it. Now, while a refracting telescope's relatively easy to make, you just need to have two lenses and a tube that you can adjust for focusing. And this is the type of telescope that Galileo used. It does suffer from some problems. Getting to be a really large aperture opening here means you have to have a relatively large lens, and those can cost quite a bit of money. The other problem is if you notice, we're coming in here with our waves of light. They're going to bend, and the different wavelengths will bend differently. So we get a problem called chromatic aberration, which means sometimes you'll get a blue halo around the object that you're looking at. So refracting telescopes are easy, they're simple to use, they don't suffer from a lot of problems, but this is one of the earlier telescopes that they did use, and this is what Galileo used to look at Jupiter and see the Galilean moons. The second type of telescope is a reflecting telescope, and these telescopes use mirrors. And what the mirrors do is they reflect the light as opposed to refract it like a lens. So what we'll notice is we have three different types here. We have a prime method of a reflecting telescope, and that's where you'll have a really large opening here, a large aperture. And that's going to allow this light to come down. It's going to bounce off of a mirror up to here, and then this is where we have our observation. So we actually do have some reflecting telescopes where you'll sit in a cage inside the telescope and you'll be able to see the images projected off the mirror that way. We can also have a Cassegrain model. The Cassegrain model will have the light come in off of a big mirror at the bottom, it'll bounce up to another mirror, and then they'll send it down through the middle. And a lot of times you'll have an eyepiece here, and you can have a lens for slight magnification and focusing there. The other type is a Newtonian one, and a Newtonian one again is going to have a lot of light come in this way. It's going to bounce up to a secondary mirror here, and then it'll shoot it out the side here, and this is where you'll have your eyepiece and lens so that you can do your focusing. And you might wonder about putting an object here in the middle of all of these to stop the light coming through, But normally with a reflecting telescope, because the mirrors are cheaper than lenses, you can have a much bigger aperture. And when you're looking at space, you want as big as aperture as you can have so you get the most light coming into your telescopes. Now the third type of telescope is a radio telescope. And a radio telescope takes in radio waves. And what that does is it's just like a light telescope, but instead of creating an image that we can see with our eyes, it's one that we have to interpret. So a lot of times we can run it through a computer and generate an image that way, or we're looking at the patterns to see what's going on. What's really cool about radio telescopes is they can be huge. In Puerto Rico, there's Arecibo telescope, and that one is built in the inside of a volcano. So you have an extinct volcano here, and what they did is they lined the inside of it so it looks like one of these radio telescopes. And they use that basically to look out into space. The problem with that one is it's always faced in the same direction. If you notice these here, they're mounted, and these mounts can spin. But also I want you to notice that there's a whole bunch here. And what they do with radio telescopes is they'll set them up in a pattern much like this. And by doing that, what you're doing is instead of only having an area this big to catch radio waves, you now have an area this big to catch radio waves. And they can actually hook these up across the planet, and you can actually make a much larger antenna to collect in these rays. So radio telescopes work great. They work during the daytime. They work during bad weather. But again, they don't produce the really high quality images that people want to look at when they see them. So the best way to get high quality images is you take your telescope and you send it out into space. And the main reason you're going to do this is you want to get rid of the atmospheric distortion. So if you can get it outside of the atmosphere, you don't have to worry about weather, you don't have to worry about day or night time, you don't have to worry about smog or clouds or any of those issues in the atmosphere. Basically, you've eliminated that problem, and that's huge. Now, the most famous space telescope that we have is the Hubble Space Telescope, and that's actually a light telescope. So when you see pictures like this, which is the Hubble Deep Sea Field, this is where they're opening it up and they're actually taking a time-lapse picture out into space. And we'll talk more about this picture a little bit later on in the course. But getting a telescope into space, it's harder to maintain. It's actually hard to get them up and out there and make sure they don't get damaged in the trip. But if you can get one out there, they work really well. We also have telescopes out there that are measuring X-rays and ultraviolet rays. But like we said, the most famous is going to be this one here, the Hubble telescope. All right, that's it for our video. As always, good luck on the quiz, and we'll see you in the next video. Aloha and welcome to our video on the sun. In this video, we'll explain the structure of the sun, we'll describe some of the physical features on the surface of the sun, and we'll explain how the sun produces energy. Okay, so let's take a look at the structure of the sun. In the center we have the core, and this is where the bulk of the nuclear reactions are happening. From here we have our radiation zone, and this is where we have the outward pressure of the explosion of all of these nuclear reactions occurring. Now, outside of the radiation zone, we get to the convective zone. And in the convective zone, you can see we have these little convective current circles here that are going. And that's going to play an important role on what we see on the surface of the sun. Now, using the term surface is really kind of interesting. If you look, we have a photosphere here, and this is going to be a boundary between the convective layer and the chromosphere here. This photosphere is what we would call the surface of the sun, but remember that the sun is just a big ball of gas, so it really doesn't have a true surface. We just have boundaries to where we're seeing these things happening. Beyond the chromosphere, we get to the corona here, and you can see that. And if we look around, we'll see some other parts of the sun as well. We have the granulation, which we'll see on the surface, and there's pictures in the lessons, but we'll show you those. We have sunspots, and we'll talk about those a little bit more. And then we also have these things called prominences. So we'll talk about those a little bit later on in the video. So if we were to look at the sun through a telescope, this is what we would see as long as we have a filter on it. Remember, if you look at a sun through the telescope, so much light's going to come through, you'll probably burn your retina. Not a good thing. But we can look through it with an appropriate filter placed on it. When we look at the sun, and this is what Galileo did, he noticed that there were blemishes on the sun. And if the sun is the most perfect thing, then according to Aristotle, it should have been a perfect sphere. And when we look at it, it is spherical in shape, but it did have those blemishes. Those blemishes were called sunspots. And if we look in the picture on this side here, we can see that we have a sunspot here. a rather large one, it's going to have an umbra, a darker part here, and then a penumbra around it. So just like our eclipses and our shadows, we talked about the true dark part is the umbra, and then kind of a lighter part being that penumbra here. We also can have some pores that we'll see there, and most sunspots are going to come in pairs, so we'll see two of them together. And then we talked about the granules, and you can see the granules down here, how it's kind of the surface of the sun is kind of granulated. And we see that because of the convective nature of the gases below. So they're kind of bubbling up and such like that nature. Now, these convective areas are going to create magnetic fields per se. So we'll have a north and a south magnetic field. And what we notice is connecting these two on the surface is where we'll see these solar arches or these prominences. And sometimes when we have this magnetic field, it'll switch around, it'll turn off, or the prominence will be so large that it'll break away like we see here, and we can have what we call a solar flare. And that's just a massive ejection of all this energy from the sun coming out at one time. And this can mess with some communications or satellites throughout the solar system as this energy rushes out away from the sun. Now here we can see another solar flare. You can see the prominence is split and it's going to break off here. One of the interesting things about these solar radiations, these massive outgassings, is when it gets into the upper levels of our atmosphere, it'll cause what we call the northern or southern lights. And you can see a really nice picture of it here. And this is when the sun's energy hits our ionosphere, the top of our atmosphere, and it causes it to radiate or glow. And that's what the northern lights would be. So we'll talk about the formation of a star in another video later on, but inside of the sun in the core is where we're seeing this nuclear fusion. And what happens in this nuclear fusion is we're going to have this hydrogen nuclei. And this hydrogen nuclei are going to come together and they're going to form helium. And it's going to be helium-3. So what we have is a hydrogen here, one proton, another hydrogen here. And now when they collide, notice we have two protons and one neutron, and that's going to form helium-3. Now, this is the first part. Notice it's releasing radiation in the form of gamma rays, but it'll release it across the entire spectrum. And then what happens is we will have two helium-3 nuclei collide. So as these two helium-3 nuclei will collide, it'll release more energy, and we form this normal helium-4 ion here. This is the nuclei part here. So this is what we're looking for, a 2 protons, 2 electrons, a helium-4 nuclei. But we also release out these extra hydrogens, and if we notice, this is part of our process here. So this is how it'll repeat the cycle until we use up all of the extra hydrogen, and that's when we'll talk about the death of a star later on in another video. Okay, as always, the lessons will go into a little more detail. Good luck on your quizzes, and we'll see you in the next lesson.